Yeah, welcome everybody. My name is Lars Lischke from the University of Stuttgart, and I'm happy today to present our work together with Paweł Woźniak, Sven, Andreas Preikschat, and Morten Fjeld from the University of Chalmers in Gothenburg. Probably all know hardware sliders probably from mixing tables or other applications to enter data. Also, we know software sliders, SUI elements to enter data, and a few years ago, Jansen et al. Showed that data input with physical sliders is better for interacting with large displays than with software sliders. And there's a bunch of work showing or arguing for force feedback or movement resistant feedback to explore data not only visual but also in a haptic way. However, there's no fundamental exploration of how is the haptic feedback perceived in such an application. Hence, we built a sliding device looking like this in a hardware way. So we have a motorized fader, known from the music industry, connected to an Arduino that we can control it and also get the data back to the computer. And the way the slider gives the feedback, that's programmable. In this case, we just had not just where the slider ticks to, so that you can feel different positions in the slider. In this case, we had 10 different positions. But I will explain this more later, detailed by the study. That the participant later on can nicely grab it, we simply printed a 3D case, simply for better handling and that it's safety to grab. Based on related work, we defined 4 different hypotheses. The first one is that we assume that the additional feedback results not in a higher task completion time when you're selecting values. The second one is that if you have visual feedback, the result or the accuracy of the result is not changing. The third one is if you can look on the input device or if you don't have direct feedback which values you enter, the additional haptic feedback will support the value selection. And lastly, we assume that the additional feedback you get in a haptic way will result in a higher mental effort if you have additionally also the visual feedback. To prove our hypothesis, we designed a user study. In this study, 17 participants participated. We used a repeated measures design with 3 independent variables. So one is a device, so we used the device I just showed you, we developed on our own. Additionally, we had an Android tablet using a software slider, looking like a sliding UI element you know from other applications. And then we varied the type of visual feedback. With visual feedback, the participant could look at the device and also the representation on the remote display. In another condition, we covered the device that the user is not able to look at the device and also showed no input position on the remote display. There we removed the condition where we use the tablet because if you don't look on the flat surface of the tablet, you are not able to select any value because you don't see it, you don't feel it, you have no choice to select any value. And finally, we had the haptic conditions. One is we have the haptic feedback, the variable we programmed or it's actuated by the motor. And if you use the sliding device, you have all the time the haptic feedback of touching the slider knob. That's also a condition we analyzed differently. The task was pretty simple. So as you can see over here, we showed the software slider on the remote display with a green arrow. The target position was displayed, and in orange we had the slider knob displayed where the user could in some conditions see where the slider knob is actually. In every condition it just presented the participant had to do 32 selections. And we started in every condition from the left position because we assumed that sliding to the left or to the right is on the short range of 10 centimeters we had for the slider is equally to the left and to the right side. As measurements, we used the task completion time. Furthermore, we used the arrow. There we had a look on the position itself. So we measured the centimeter or the millimeter distance from the target. We had a look on how far the participants moved back the slider or moved around the position. So when this first time crossed the target position and then moved back, we counted this distance. And in the end, we asked the participants to rate the mental effort on this max scale to assess how complex the task mentally was for the user. Now coming to the results. In terms of the task completion time, we found significant differences when no visual feedback was presented. In these cases, participants were slower with the additional haptic feedback in comparison to the simply touch only the physical device condition. In all other conditions, we found no significant difference. So when visual feedback was presented, there was no differences in the task completion time. When we are looking on the error, it's pretty obvious if you don't have visual feedback, the result has a higher error because, well, you can only feel where your slider knob is at the moment. And in conditions where we don't have visual feedback, the accuracy was much better and significantly better when we had additionally the movement resistance feedback. When we are looking on the backtracking, we had differences between the condition where we had visual feedback and we had no visual feedback. Obviously, again, when no visual feedback was presented, users were more unsure about the position and corrected more. But more interestingly, we had also significant differences between the device type. So when the user used the touch display, they corrected much more than with the physical device in both cases. So as you can see over here, the correcting distance was around 5.5 millimeters on the touch display and around roughly 2, not sure, 2 on the physical device. And finally, the mental effort. Again, when we had no visual feedback, the task was more demanding than we had visual feedback. That's also pretty obvious because you have to concentrate more on your haptic feeling, and we are all trained to do visual tasks, so that's pretty clear. But over here, it's interesting. If you have the additional movement resistance feedback, it's not as demanding as you don't have this additional feedback. So to come back to our hypothesis, we see an influence of the task completion time depending on the feedback. So if there's no visual feedback, the task completion time is increased. So we have to say, in some cases, our first hypothesis is true. The second hypothesis, that the result is not interfering when there's visual feedback, is true. So we saw the differences if you have visual feedback. It does not make any difference if you have additional haptic feedback, which is also, again, clear because we are trained to look at the visual feedback more than on the haptic feedback. But interestingly, or luckily, the third hypothesis is also true. If we can look on the device or get directly feedback, which is often the case if we're exploring complex content, in particular in large displays, then we don't want to look on the input device, and then we are better if we have additional haptic feedback. Our last hypothesis that it's more demanding to have additional haptic feedback to the visual feedback is not true. We don't see there any significant differences, so we can also reject this hypothesis, which is also nice because it creates not more mental effort for the user to get additional feedback. As I presented already, the form factor has also an influence on it, but in this study we just, as a first step, we looked on the feedback methodology and not on the form factor. So we printed one case, but definitely depending on the application and on the task the user is performing, many other form factors would be possible. So that's something we plan to explore further in the next steps. So for example, you can have something round with multiple sliders that you cannot see all the sliders at once. You can have 2 or whatever design you might imagine. To come to the future work, as I already said, the form factor is one thing we will explore deeper. Oh, sorry, I missed one slide. And then furthermore, the different patterns of the feedback is one thing we do not analyze in the first study, so definitely you can program different feedback functions for the haptic feedback. And finally, I would like to summarize my talk. We presented the first fundamental understanding of how movement-resistant or forced feedback for sliders is perceived by the user. We showed that the physical sliding causes a higher task completion time. However, if the user is not able to look at this input device or get directly visual feedback, the accuracy is higher with haptic feedback in comparison to touch input or sliding only the physical device. Thank you very much.
Thank you, Lars. We have some time for questions.
Hi, I'm Ben Bengler, University College London. I just wanted to ask you, have you looked into industrial work that uses these kind of mechanisms? So I remember there were devices around 2007, Immersion had this dial that you could program with, to have dense or to have several behaviors, and I think devices like that then moved heavily in the car industry, like BMW iDrive uses these kind of mechanisms to help users with haptic feedback to navigate through menus. Yeah. And I was wondering, have you found any, or could you find any research that has been done on this topic, because it seems to be used since a long time.
There's a lot of applications proposed, so ranging from education to exploring 3D data, but there's no fundamental understanding how users perceive this feedback.
Okay, thank you.
So, yeah.
So, Lars, I was surprised that you looked only at visual output when the examples you give of tangible devices seem like sound slider, like soundboards. Do you think your results would change if they were controlling something, some other modality, so sound, for instance, versus visual output?
Yeah, I think also for other than visual output, it's interesting. But in our case, if you look at the related work where people analyzed not linear sliding, but for example, rotary knobs, they are also looking on visual. So we aimed in the first step to present some comparable work that it's easier to understand. But definitely audio output is another way to go.
Okay, thank you. Are there any final questions? Okay, let's thank the speaker. Thank you.